Let's talk Newton's third law. A little bit of tension and a little bit of normal force today. Okay, I know you guys did that lab yesterday where you smashed the two carts into each other, and no matter what you did, you always saw that the two forces were equal and opposite. Okay, and most people say Newton's third law says that for every action there's an equal and opposite reaction, and I absolutely hate that. Okay, not because it's not accurate, but because it's not accurate enough. Okay? We need to go a little bit further into it. Okay? So Newton's third law really focuses on two things. Okay? Remember in the beginning we said that every force has an agent. Okay? The agent is what exerts the force. When you lift a book, you're the agent. You exert a force on the book, you cause it to move. Okay? When you get pulled to the ground by gravity, gravity's the agent. Okay, it exerts a force on you, it holds you to the ground. Newton's third law involves the agent and the object. And here's what Newton's third law says. It says, when one object exerts a force on another, the second object, okay, so it's important to keep that in mind. When one object exerts a force on another for a second, okay, on a second object, we have two things here. When one object exerts a force on a second object, the second pushes back on the first with an equal but opposite force. Okay. Now, you guys are familiar with this if you've ever been, say, skating or really running or doing anything. When you jump, say you're in a jump, what do? Well, you push down on the ground. So here's my person hanging out there on the ground. Now, at rest, okay, at rest there's two forces acting. There's gravity, which is pulling down, and there's the normal force, the force of the ground, that pushes up. Now I want you to think about it. Okay? Whoops, that's not Fg, that's Fn, normal force. Okay? When you jump, what can push up on you? Your feet push down. You can push down. Okay? Which one of these can push up? Well, gravity always pulls down. So when you first jump, you bend your knees a little bit, and then you push down on the ground. Okay? How does that make you go up? It doesn't. The ground pushes back on you. So your force causes a reaction force. Okay? So this reaction force is what actually pushes you up. It's the equal and opposite force that the ground pushes back on you. Okay? Now, maybe a clear example. Okay, you guys are all familiar with the Newton's apple story, right? Newton was all about how gravity is universal when he's sitting under an apple tree. And he's like, oh look, here's my apple tree, and I'm watching this pretty little apple, and it's hanging right here. Okay, and it decides to fall. Well, it doesn't decide to fall. Gravity causes it to fall, right? That's what Newton's famous for. He's like, oh, the same force that holds that and pulls that to the ground is the force that holds the planets in orbit, whatever. Okay. Well, if this force of gravity, what causes it? This is the force, really. That's the force of Earth, right? Earth's gravity, force of Earth on the apple. Okay? Well, according to Newton's third law, then, the apple actually exerts a force back on the Earth, and it's equal in size and opposite in direction. So how come we don't notice the Earth accelerate? Well, the mass of the Earth is huge compared to the mass of the apple, so it's just, okay, it's too small to even care about. Too small to measure, too small to notice. Okay? But Newton's third law says there's actually, because of this force, there's a force on the Earth, equal in size, opposite in direction. So the two are actually accelerating towards each other. Now, what about Newton's third law then when you have a book sitting on a table? Right? Wow, that's a really horrible table. Okay, so let's try that again. So you got a book sitting on a table. That's so not much better. Okay. What forces act on that book or that block or whatever it is? Okay, normally we think there's two forces, okay, because we're talking about the table or the block. Okay, there's the force due to gravity and then there's the normal force. Okay? That's true. What exerts the normal force? Well, the normal force is exerted by the surface, by the table, on the object. Okay? That means that this object is actually exerting a force back on the table, which makes sense. Okay? Gravity's pulling down on the block, and so the block's actually pulling up on Earth. Okay? So there's actually a couple more forces going on here. Now, I'm not going to get too carried away about trying to find all these things and label all the forces, one object on the other, the first object back on the second. But you should be aware of it. In some situations, it's kind of a big deal. Okay? When you go ice skating or something and two people push into each other, okay, they're going to have the same force. The first person exerts a force on the second, and the second person exerts that equal force back on the first. So they're going to move apart, not necessarily at the same speed, but with the same force. Okay, and so let's illustrate what I mean by that. Remember, we're going to use Newton's third law and Newton's second law together. So I have a person, well, two people, and they're on a frictionless surface. They're ice skaters. They're happy. Okay, this person and this person. So person one, person two. Okay, these two people push against each other. Okay, and so let's say that this person over here has a mass 60 kilograms. This person over here has a mass of 50 kilograms. Okay? And this person, the guy on the right, pushes this way on the second person with a force of 100 newtons, say. It's 25 pounds, pushing pretty hard. Okay, all right. So 100 newtons is applied to this person. So I'm actually going to go ahead and I'm going to put that arrow over here because that force acts on that person. Well, according to Newton's third law, an equal but opposite force acts back. Okay, so the red guy pushes on the black stick figure there with 100 newtons of force, and so automatically we know there's also a 100 Newton force acting this way. You'll notice those two forces don't both act on the same person. If they did, nobody would move. Okay, so this 100 Newton force acts backwards, and so we're going to say, okay, well, we want to know that guy's acceleration, and we're going to assume the only force in the horizontal direction is that 100 Newton force. They're ice skaters, there's no friction. Okay, so net force equals mass times acceleration, and so 100 equals 50 times A, and so A equals 2 meters per second, except this 100 Newton force is to the left, so I'm going to call it negative, which makes this negative, which makes this negative. So this guy accelerates to the left, or negative 2 meters per second. Okay, well, what if we jump over here to the red skater? Well, net force is still mass times acceleration. This time, the force is a positive 100 newtons. The mass is 60. What's the acceleration? Well, we divide by 60, and we get our acceleration is equal to 1.6666 meters per second. Okay, and so you can see just because they have equal forces on them doesn't mean they move with the same acceleration. This is why it's still better to be the big truck on the interstate, right? Yeah, okay, so you get hit by a little car, you experience equal and opposite forces, but the big thing doesn't accelerate as much. So you sitting in the passenger seat or the driver's seat, doesn't matter, aren't going to feel as much as the person in the little car. Okay, and so that's a Newton's third law thing as well. Now, last thing I want to take a look at is Newton's laws applied to a few different scenarios. Okay, so I'm looking in the book on page 107, and I'm going to assign some problems after this. I want to work a few, and then I want you guys to work it through. So page 107, I'm looking at number 36. Okay, and the problem says a block hangs from the ceiling by a massless rope. Okay, so we need a ceiling and we need a rope. We're always going to assume massless ropes. If the ropes have mass, the problems get tricky in a hurry. Okay, so massless rope. A second block is attached to the first block and hangs from it on another piece of massless rope. So now I need a second block and a second rope. Okay, so two blocks hanging from the ceiling. If each of the two blocks has a mass of 5 kilograms, so 5 kilograms, we're supposed to find the tension in each rope. Okay? Well, we've got multiple objects here, so we're going to look at each object individually and identify all the forces. Okay? So if we look at this object here, there's two forces acting on it. Okay? There's the force due to gravity, Fg, and the tension in the rope, Ft. But since it's just hanging there, we can say Ft plus Fg equals 0, because the net force has to equal 0 because the acceleration equals 0. Okay? Which means we can say Ft is equal to the opposite of Fg, if we subtract that over, which is equal to, well, Fg is equal to mg, okay, but this would be negative mg, okay? But then g is equal to negative 9.8, I'm assuming down is negative, okay? So this is equal to negative m times negative 9.8, and since m is 5, this thing is 5 times negative 9.8, but it's negative negative, and so this equals 49 newtons. Okay? So there's 49 newtons of tension in this rope. Okay? What about in this rope? Is it also 49? No. There's two ways to go about solving this problem. You can say, well, let's look at this one. Okay? Let's look at this object. Again, there's two forces, except there's really more. Okay, so let's zoom in on this object. Okay, so this is the top block. There's the tension in the rope. Okay, because there's 49 newtons pulling up on this end of it, there's 49 newtons pulling down on it. Okay, but there's another 49 newtons pulling down on it. This is gravity. Okay, so there's actually two forces acting on the top block. There's the force due to gravity, and there's the 49 newtons that this block exerts on it, which means this thing, this tension up here, has to support both. And since we know this is a 5 kilogram block, we know this is also 49, and so really what we have is this tension force is 98 newtons. Now that might be a complicated way of looking at it. You might just say, well, the top rope is supporting 10 kilograms of mass, and so 10 times 9.8 is 98 newtons. That's true. Okay, and the bottom rope is supporting 5 kilograms of mass, and so the bottom rope, 5 times 9.8, 49 newtons. That's true. Okay, but there's internal forces, okay, they're there, and you can find how much tension's in that rope. Kind of an interesting way of doing things. There's a simple way, and there's the more complex way, but both get you the right answer in the end. The other one I want to look at on this same page is number 38. Number 38 says, and this one's about the normal force. It says we've got a person standing on a surface, okay, and this person has a mass of 61 kilograms. 61 kilograms. And somebody hands them a box, and so now they're also holding a box, and the box has a mass of 13 kilograms. 13 kilograms. Okay? And we're supposed to find the normal force exerted by the force up, okay, the normal force exerted by this surface on this person. Okay? Well, it's just a normal force problem, right? Net force equals mass times acceleration, and if the acceleration is 0, then the net force is also equal to 0. Okay, so the net force is the sum of the forces, and we got to label them all. Okay, and so we can say, well, there's this force that's pulling down. This is the force of gravity on the box, and then of course then there's got to be a force up. This is the force from the person that's holding the block. Okay, but then this person is exerting a force. Gravity's pulling down on them. Fg is on them as well. I'm going to call it G2 since it's different than this one. And then there's the normal force here, Fn2. Okay, now the normal force here is not just supporting the person, because Newton's third law says, well, if the person pushes up on the block pushes down on the person, and that force is going to be transmitted down. So to me, it's easy not to think about it as two different objects. To me, it's easiest to say, well, there's a total of 74 kilograms there. Okay. We need to support it all. Gravity pulls on that with an acceleration of 9.8 meters per second per second. Okay, and so our normal force that this surface has to exert is going to be equal to 74 times 9.8. 725 newtons, and we're done. Okay, and so that's Newton's first and second law. Now what I want you guys to do today, and Newton's third law, is I want you to look at page 113, and I want you to work problems 59, 61, 67, 68, 70, which I kind of already did for you guys in another video, 84, 86, 89, 90, and 92. I'm going to put a little star by 92. This problem's tricky. Okay, we're going to do a lab on it tomorrow. See if you can figure out what's going on with it right now, today. Okay, good luck. Email me or come see me in homeroom if you have questions, except today's a pep rally, I think, so you can't really see me in homeroom.